Hello students, welcome to Vishweshwara Technological University's first semester Basic Electronics. This is class 5. Here we will discuss about operational amplifiers. In short, we can call it as op amps. Amplifier, already we have discussed. Amplifiers is an electronic circuit which increases the strength of a weak signal. Amplifier increases the strength of a weak signal. So if this is the input, so the strength, the amplitude will increase. So that is the meaning of an amplifier. Then what is this operational amplifier? What is this operational amplifier? This op amp, usually it is popularly called as op amp, operational amplifier. This op amp, in addition to the amplification of the AC signals, it can also do some mathematical operation. That is, it can add, it can subtract, it can integrate, it can differentiate, it can be used for comparison purpose also. So it can be used for different operations, mathematical operations like addition, subtraction, integration, differentiation, and also for the comparison. So the name operational amplifiers. The symbol for the operational amplifier is this. Here it has two inputs. One is inverting input, This is non-inverting input, one output terminal, and it will have the supply voltages. Usually this will be plus 15 volts, here minus 15 volts. It requires a symmetrical supply of plus or minus 15 volts. I repeat, the operational amplifier symbol is this. It has two terminals. One is inverting input terminal, other one is non-inverting terminal, and one output terminal. Usually it will have a symmetrical supply, equal and opposite, plus 15, here minus 15 volts. This diagram shows how the supply connections would appear if we decided to include them. Usually even if you don't include positive supply and negative supply, there is no issue. But it is better to write here plus positive supply and negative supply. In a bigger circuit, if the circuit diagram is a huge, then we can neglect this. But by neglecting this doesn't mean that we don't connect the supply, but always the supply will be there. So how this supply looks? So this is nothing but a power supply of equal and opposite. Here you can see a series of power supplies, positive, negative, negative. The positive terminal is connected to plus VSS, positive supply rail. Here the negative terminal is connected to the negative supply, plus 15 here, minus 15 here. Then the common terminal here, this is the common 0 volts rail. So whatever the components you connect to the inverting terminal and non-inverting terminal, definitely they will have the common terminal to connect it to this one. So always with respect to the common terminal, we apply the voltages to the inverting and the non-inverting terminal. Let us see some of the parameters of the operational amplifier. Important parameters. Open loop voltage gain. As you know, gain is nothing but output by input. Voltage gain means output voltage by input voltage. Open loop means there will be no feedback. in the open loop voltage gain. Ideally, the open loop voltage gain is infinity, but practically it will be in the range of 1 lakh, or it may be greater than this. So the open loop, here OL stands for open loop. The open loop voltage gain is given by V out by V in. It is a voltage ratio, volts by volts, so there is no unit. This is the open loop output voltage, this is open loop input voltage, so open loop voltage gain. So there is no unit for this. Ideally, remember, always it will be infinite. Ideal voltage gain is infinity. Practically it will be greater than 1 lakh. This value itself is a very larger value. Usually this open loop voltage gain is expressed in decibels. If you observe here, D is small letter, B is capital letter. This Bell is nothing but Alexander Graham Bell, who invented the telephone. So here this is the name of a person, so always you must write B capital. So decibel. So if you want to express this open loop voltage gain in decibels, so we can calculate 20 log V out by V in, 20 log V out by V in, then this will be in decibels. So either you can go with the ratio or you can express the open loop voltage gain in decibels. Usually we tend to express the open loop voltage gain in decibels. Then usually the normal range will have the 90 decibels or even more than that. So this is about the open loop voltage gain. Remember, open loop, there is no feedback. Gain output by input, voltage gain output voltage by input voltage. If there is a ratio, remember there will be no unit. So we can also express in decibels by calculating 20 log V0 by Vin. Just similar to the open loop voltage gain, closed loop voltage gain. Now then only this word changes. Closed means there is a feedback. There is a feedback. Feedback means some portion of the output is fed back as the input. So closed loop voltage gain is nothing but the ratio of the output voltage to the input voltage when there is a feedback. When there is a feedback, usually this feedback will be negative feedback, because the gain of this operational amplifier is very large. To decrease this, so we will go for the negative feedback. So where AVCL is the open loop voltage gain, V out and V in are the output and input voltages respectively. The closed loop voltage gain is normally very much less than the open loop voltage gain. So open loop voltage gain is very larger than the closed loop voltage gain. To decrease the open loop voltage gain, we will apply the feedback, so it becomes a closed loop, so the gain decreases. Here also you can go for expressing the gain in decibels by taking 20 log V out by V in. So here is a simple example, just like a LKG problem. An operational amplifier operating with negative feedback produces an output voltage of 2 volts. Output voltage of 2 volts. When supplied with an input voltage of 400 microvolts, determine the value of closed loop voltage gain. Closed loop voltage gain is given by V out by V in. V out is 2 volts, input is 400 microvolts. So if you calculate, you will get 5000. You can observe we have not written any unit there. Usually the voltage gain is expressed in decibels, so take 20 log of 5000, you will get 74 decibels. Then one more parameter, input resistance. Resistance, everybody knows, it is a ratio of voltage to the current, because we are fully aware of the Ohm's law and we frequently use Ohm's law. So you should not forget Ohm's law and Kirchhoff's voltage law, Kirchhoff's current law. Everywhere we use. So Ohm's law, resistance R is equal to V by I. Input, so input resistance is equal to the ratio of input voltage to input current. Definitely unit is ohms. Ideally the input resistance is infinity, but practically it will be in the range of mega ohms. Output resistance, once again very simple, Ohm's law, output voltage to the input voltage. But here we will take open circuit output voltage to short circuit output current. Current flows in a closed path, so here is a short circuit. Here we measure the output voltage. We open it and measure it. So open circuit output voltage to the short circuit output current. Once again the unit is ohms. Then what will be the ideal value of this output resistance? Output resistance ideal value is 0. But practically it ranges in the value of from 10 ohms to 100 ohms. Very small value, because ideally it is 0. Input offset voltage. So we'll go back to the symbol. This is a symbol of the operational amplifier. Inverting input terminal, non-inverting input terminal, inverting input terminal, non-inverting input terminal. Here is the output terminal. Suppose if I apply 1 volt here and 1 volt here. This 1 volt I am applying it to the non-inverting terminal. This 1 volt to the inverting input terminal. So 1 volt minus 1 volt. So this is 0 volts. So this operational amplifier is a differential amplifier which amplifies the difference between these two input signals. So it should amplify this 0 volts, whether its gain is 100, 50 or 1000 or infinity. So if you amplify this, definitely you should get 0 ideally. But due to imperfect internal balance, always you will get a small voltage at the output. Very small voltage. I repeat, an ideal operational amplifier would provide 0 output voltage when 0 difference is applied to its inputs. So the difference is 0 here. When you apply 0 input voltage, 1 volt, 1 volt, the difference is 0. Or you can go for 2 volts, 2 volts, the difference is 0. So if you amplify the difference, definitely you should get a 0. But due to imperfect internal balance, always some voltage is present at the output. Then to make the output voltage 0, we apply some voltage, for example 1 millivolt to 15 millivolts. So the difference here, we apply the voltage 1 millivolt to 15 millivolts to make output voltage perfectly 0. So this voltage is called as the input offset voltage. The voltage that must be applied differentially to the operational amplifier in order to make the output voltage exactly 0 is known as the input offset voltage. I repeat, the voltage that must be applied differentially to the operational amplifier input in order to make the output voltage exactly 0 is known as the input offset voltage. Usually its range is 1 millivolt to 15 millivolt. So this is the input offset voltage. Full power bandwidth. You know what is bandwidth. What is bandwidth? If you consider this as a frequency response, this is a voltage gain. So how do you find out the bandwidth? In the previous videos we have seen. So we will plot a line of 0.707 of 0.707 of AV, or 70.7% of the maximum gain, mid-band gain. So somewhere here, approximately somewhere here you will get. Then here it intersects, so we will call it as lower cutoff frequency. Here it intersects, so we call it as a upper cutoff frequency. Bandwidth is nothing but F2 minus F1. Bandwidth is nothing but F2 minus F1. Typical full power bandwidth ranges from 10 kilohertz to 1 megahertz. Ideally this bandwidth is infinity. Then slew rate. Slew rate is the rate of change of output voltage with time. Slew rate is the rate of change of output voltage with time when a rectangular step input voltage is applied. Usually the unit is volts per microseconds. Volts per microseconds. So here we will see the slew rate. We will apply the input. A step input. Here there is a step input. Observe here where we have applied. Usually the input is applied to the inverting terminal. Unless otherwise specified, always assume the input is applied to the inverting terminal. If you apply input to the inverting terminal, something like this, so it gets inverted here. If you apply the input to the non-inverting terminal, it won't get inverted. The same thing you will get. It will be in phase. Anything you apply, suppose if you apply to the inverting terminal, it gets inverted. That is a name. Inverting. It inverts. So in the slew rate also, we will assume the step input is applied to the inverting input terminal. So usually what we expect, if this is the input, the output also should change like this. Because slew rate is rate of change of output voltage with time. So how much time it takes? So if it is ideal, ideally slew rate is infinity. If it is ideal, definitely it should have changed here itself. But here it is not ideal case, so it takes some time. It takes some time to reach the required or the destination here, the output voltage. So it is taking this much of time. But if you observe here we have written like this, from negative to positive, but actually it should have been from positive to negative, but we understand like this. But as we have applied the input to the inverting terminal, so the slew rate, the step input, the output response for the rectangular signal is coming like this. Repeat. So this is a step input applied to the inverting terminal. So we have written the output. So here, see, this has got inverted. This we have written here because we have applied it to the inverting input terminal. Here the output we expect to fall here itself, but actually it takes some time. But here, as the input is applied to the inverting terminal, we will invert this, so it is going from negative to positive. I think this is clear. The slew rate is the rate of change of output voltage when a step input is applied. So here few more things given. Let us go through this. The open loop voltage gain must be very high. The open loop voltage gain must be very high, but ideally it is infinite. The input resistance ideally infinity, but actually it is very high. The output resistance ideally 0, but it is of very low value. Full power bandwidth usually infinity, practically it is very high. Slew rate should be as large as possible, because within no time the output should follow the input. Input offset should be as small as possible. So this table will give you the comparison between the ideal and real values. Just now we discussed the voltage gain ideally is infinity, real value is 1 lakh. Input resistance is infinity, but real value is 100 mega ohms. Output resistance ideally 0, actually it is very small value, ranges from 10 ohms to 100 ohms. So practically you can take it as 20 ohms. Bandwidth is infinite ideally, practically it ranges around 2 megahertz. Slew rate ideally infinity, but actually it goes to 10 volts per microsecond. So input offset voltage ideally it is 0, but actually it is less than 5 millivolts. Thank you.